to present some talk about interface motion from a non-gradient Glauber-Kawasaki dynamics.
Okay. Thank you very much, Cedric, and the very kind invitation to talk in the Moscow Probability and Analysis Seminar. So actually, I once visited Moscow a long time ago in 1989 at the Evolution Seminar. So it just reminded me a very good memory at that time. So today I want to talk about interface motion from non-gradient Glauber-Kawasaki dynamics. So this is mostly the probability topics, but I also touch some nonlinear PD problem. Okay, so the motivation comes from the statistical physics, non-equilibrium statistical physics. It is related to the dynamic phase transition, or sometimes also called the dynamic phase separation. And phase transition is discussed mostly for the equilibrium case, for the, say, in the Ising model. So the related to the Ising model, maybe the Kawasaki dynamics, that is also called the exclusion process. At low temperature would be a desirable model to discuss the dynamic phase transition. But it is still out of reach. So there is one result by Baradan and Yao already long time ago. They proved the hydrodynamic limit, but only at a high temperature case. So I learned this problem from Kawasaki. They wrote a paper starting from not particle system, but SPD model. Which is actually mathematically, it is called the dynamic P5 model. They study in the 3D case. Or sometimes it is called the stochastic Allen-Kern equation, or the stochastic reaction diffusion equation. And SPD model is a bit easier. That actually Kawasaki right. And starting from SPDE, they just derived mean curvature flow to separate. There are two phases actually related to this SPD, stochastic PD, and they derived at a macroscopic level mean curvature flow, but still keeping some noise. So instead, this SPDE is considered as a mesoscopic level in a sense. So we have a microscopic model which corresponds to this SPDE, that is Glauber-Kawasaki dynamics. Kawasaki dynamics correspond to the, say, the Laplacian, and Glauber correspond to the nonlinear reaction term. Therefore, microscopically, it is interesting to start from the Glauber-Kawasaki dynamics that I want to discuss today. So our goal is starting from microscopic interacting particle systems, that is a Glauber-Kawasaki dynamics, or we can say it's just Kawasaki part correspond to random walks. So you can relate to the Laplacian. And the Glauber part, that is a creation and annihilation of the particle, and we consider on the discrete lattice. Then choosing these rates, creation and annihilation rates, in a sense, we have to tune. We have to tune. Then we have a situation that autonomous separation into two phases, dense area and sparse area. But we have to choose, as I said, creation and annihilation rate in a proper way. But if we choose properly, then we automatically, actually starting from a very chaotic situation in a very short time, like uh, almost time zero, we observe autonomous separation into dense area or sparse area microscopically. Then we discuss a hydrodynamic limit. That is scaling from the microscopic to macroscopic. We just observe this from microscopic viewpoint, then actually this phase separation curve in the maybe 2D case or the surface, in the higher dimensional case, becomes very sharp. Then we observe some, say, curve or the hypersurface in the higher dimensional case, and we will show that this gamma t, that is this interface, actually move as an anisotropic curvature flow. So anisotropic means direction-dependent force we have. If it is uniform, then we have a mean curvature flow. But in general, we observe anisotropic curvature flow in the limit. So probabilistically, it corresponds to the law of large number. Therefore, it's interesting to consider the fluctuation of this interface, looking at the slightly different scaling. Then we will observe a linear stochastic differential equation for the fluctuation. And also, it is still not done, but I expect certain nonlinear stochastic PD appears under a certain scaling. That is also interesting, but this part is still not done. Sorry, I forgot to say. This is a joint work with Chen Gu and Han Wan. They are in the Tsinghua University in Beijing. And also PD part with Hyunjun Park. He's a Korean, but he's now in Tokyo, and he's working at the Meiji University. And also fluctuation part, fluctuation of the interface. I work with Claudio Landim in Brazil, and also Sundar Sesuraman in the US. Sorry, I didn't say, but so this is the motivation of my talk today. And okay, so I just gathered their pictures. Chen Gu and Han Wan from the Tsinghua University, and Hyunjun Park in the Meiji University, and Claudio Landim in the IMPA, and Sundar Sesuraman and in the University of Arizona. So plan of the talk. So in the first section, I just give the dynamics, microscopic dynamics, which is called the Glauber-Kawasaki dynamics. And it's scaling from microscopic to macroscopic. Then we discuss the hydrodynamic limit. This is a law of large number, but under the certain averaging effect or the local ergodicity through the via the local equilibrium states. And that is called the hydrodynamic limit. And also we can give a convergence rate of the hydrodynamic limit. That is called a quantitative hydrodynamic limit. And then we will derive the interface motion. So this section is divided in probabilistic part and also PD part. And then last section, I want to discuss the fluctuation of the interfaces. So this is a plan. Okay, so what is Glauber-Kawasaki dynamics? So it was proposed by Glauber in 1963. So he considered some dynamics, time-dependent statistics of the Ising model. So he just introduced some time evolution, a random time evolution corresponding to the Ising model. So Ising model becomes the invariant measure or the actual reversible measure. And Glauber's case, there was no conservation law, but the Kawasaki considered a different time evolution corresponding to the Ising model, but he introduced a conservation law. The number of the plus spin conserved under the Kawasaki case, but the Glauber case, it is not conserved. So they introduced such model. So the spin going up and going down, sometimes going up, changes to the down randomly, that is a Glauber case. But in the Kawasaki case, going up and going down, then once this going down, then the neighboring side, the spin changes also going up. Therefore, the total number of the spins up, and the direction to the up, conserved in this case. Okay, but we can also consider this model as a particle system. So we interpret. So Glauber-Kawasaki dynamics is originally a dynamical easing model. So we also Glauber-Kawasaki means we consider both effect at the same time. So it is a dynamical easing model, but we can interpret it as a interacting random walk that correspond to the Kawasaki part. So, okay, so we have this picture. So on the discrete lattice, square lattice, actually we only consider under the periodic boundary condition. Therefore, the lattice is just the size of the side length is n, and then we consider the d-dimensional case. But the boundary, this boundary and these boundaries are identified, and also this one and this one identified. Okay, then we put circles. Circle means sites occupied by particles, or the originally circle means upward, up-directed spins. And there is, if there is no part, no circle, then this site has no particles. Or originally, the spins on these sides is going down. But anyway, easing case, usually we consider +1 or -1. But we can consider it as a 0 and 1. And then we interpret if eta x, so we denote the all configurations by eta. Eta is a collection of the eta x. For each eta x takes a value 0 or 1. And eta x equals 0 means that there is no particle, or the site x is vacant. Or eta x equals 1 means the site x is occupied by a particle. But only one particle can occupy. It's no more than two. So we introduce the exclusion rule. That is also the hardcore interaction. So only at most only one particle can occupy each side, not two particles. So that is also called the exclusion process in probability theory. And Kawasaki case, actually, as I said, the spin going up and spin going down just interchange. That means as a particle picture, a particle occupying here jump to the neighboring sites. That is a random walk. Therefore, we can interpret Kawasaki dynamics as a random walk. Also, we will introduce certain interaction among the particles. And the Grabber one is just upward spin can randomly change to the downward spin. That is, if there is a particle here, then sometimes it disappears. That is the annihilation of the particles. And also the non-occupied side, maybe -1 and going to +1, that is a creation. Or we denote it's a 0 or 1. So 0 changes to 1, that is a creation. And 1 changes to 0, that is an annihilation. So that is, we introduce a random mechanisms for this dynamics. Okay, then, so in the probability theory, we write in this way. So this is the generator of the Kawasaki part. So pi xy denotes the exchange operator of the configuration at the x and y. So We start from eta. Eta is a configuration on the torus, discrete torus. Then we denote by eta super x, comma y. That is defined from this eta by exchanging the value of the eta x and eta y. So eta changes or the jumps to the eta xy, but with a certain speed. With the speed is given by this this function. So function c x y eta. So it depends on the configuration eta, and therefore this gives some interaction. So the exchanging rate is given by this, but it depends on the configuration eta. So a particle at x and y look around other configurations. Then the speed is determined. This gives interaction among the particle. Okay, so this is called the generator, or maybe if you don't know much about that, so then you, as usual, maybe you can consider the semigroup corresponding to this generator on the function space on the Xn. That gives a corresponding semigroup actually. And we assume the jump rates Cxy satisfy these three conditions. First one is a non-degeneracy and also finite ranginess. Non-degeneracy means always this is positive. And but finite ranginess means this one depends on eta, but not very far from the x and y. So it depends only on the eta within the distance from x within the certain distance r. Otherwise, there is no interaction. So particle look around only the distance within the situation of the eta within the distance r. So we assume there exists some constant, positive constant r, and the c depends only on this one. We assume that this condition, and also this transition mechanism is actually the spatially homogeneous. Spatially homogeneous means this is exchange rate or the jump rate at the origin to the neighboring side. But if you look at the different x, then just shifting this function. So tau x I didn't write very carefully, but this is a shift operator acting on the eta. And then it acts on also the function of the eta. Therefore, the transition mechanism is spatially homogeneous. And also the third one is a detailed balance condition under the Bernoulli measure, new law. Bernoulli measure is a product measure on the configuration space Xn. Configuration space Xn is just this one. So it's a product space. And then if the site X, so in a probabilistically, if X is different under this measure new law, these are independent random variables because it's a product measure. So we assume this condition. And this detailed balance condition is actually equivalent to say that this function Cxy eta doesn't depend on the eta x and eta y. But it depends on the other, maybe eta z. Z is not x and y. Then it depends. So under this condition, we can show that the dynamics corresponding to this generator LE. I write LE because it just the exclusion to denote the exclusion. And then this measure, new law, actually becomes an invariant measure or the equilibrium measure or even a reversible measure. Okay, so because Kawasaki dynamics has a conservation law, because the particle number is conserved, invariant measure is not unique. So we have a one parameter family of the invariant measures, parameterized by the mean law. That is a mean density of the particles. So rho equals zero means actually new zero means just there is no particle. New one means all sites are occupied by particles. And rho equal one half, for example, then and half and half. Okay, so then corresponding to the okay, the conserved quantity, we have this one parameter family of the invariant measure. To discuss the hydrodynamic limit, this is very important indeed. Okay. Then maybe I can explain the global part. Sorry, it's, something is covered. Sorry. Sorry. Okay, so the next one is the global part. So global generator we denote by LG. That is the sum of the flip operator, which is different from the exchange operator. Flip operator means from eta to transition is from eta to eta x. Eta x is defined from the configuration eta, just flipping 0 to 1 at x in eta. So if eta x equals 0, then after from eta, if eta sub x is 0, then under new configuration, at the position x, it becomes 1. Originally, it is 1. Then in the new configuration, it becomes 0. So just flipping 0 to 1 and also 1 to 0. This means 0 to 1 means creation of the particle at the position x, and 1 to 0 means annihilation of the particle at the position x. So this is called the flip operator, and we give a speed. But also this depends on the configuration eta. Therefore, this gives interactions among the particles. So this flip happens with the speed cx eta. So if c is large, then this flips happens more frequently. If c is small, then this flip happens more slowly. And again, we assume the spatial homogeneity for this flip rate, and also the finite rangeness, the interactions among the particles. We observe only within the finite distance, r, again r, maybe I don't write. And if eta 0 equals 0, so at the origin, so C eta denotes at the origin. So, okay, so simply C means this flip rate at the origin. And then if eta 0 equals 0, then this gives a creation rate. And if eta 0 equals 1, there is already a particle. Then this flip rate gives the annihilation rate of the particle at the origin. And as I said at the beginning, we have to tune this flip rate. And these flip rates are set to favor two levels of the particle densities, low plus and low minus, called the sparse and dense. And two phases have the same degree of the stability, so balance condition. I will explain later, but we have to choose this flip rate very carefully to discuss the interface problem. So these are setting. Then we consider, sorry, so maybe this is not visible. Okay, the scaling from microscopic to macroscopic. So we introduce the scaling in time and space and also mass. So the global Kawasaki dynamics is a microscopic system. and the size of the space that is denoted by n. So n is very large. And therefore, we have many particles. But we move from microscopic to macroscopic size, just changing the spatial size by dividing by n. So originally, the size of the microscopic system, the spatial size is n, but by dividing by n, the size becomes order 1. And at the same time, we introduce the time change. The time change means n square to the Kawasaki part. And also another scaling to the k, we will write k, but the k depends also n. But we put the k of n, so the time change, n square to the Kawasaki part. That is actually the diffusive scaling. So space is huge, but time is also, according to this scaling in space, we change the time to the n square. We consider much, much longer time. So this n to the, or maybe 1 over n to the n square, that is called the diffusive scaling. For example, if you have a single particle forming just a random walk, then by the so-called the Donska's invariance principle, we can observe the Brownian motion under this scaling. So you just change the spatial size by dividing by n. At the same time, if you change that time to the n square, then from the random walk, you observe the Brownian motion. So and the scaling is similar here. Then for the grabber part, actually grabber part moves much faster than the Kawasaki part. Kawasaki part has a conservation law, therefore actually grabber part just move much faster. Therefore, time change should be much slower than n square, but still we introduce the time change. K, simply we write k, but the k depends on n. But it should be much, much smaller than n squared, but it goes to infinity. So we consider this scaling in time. Okay, so but mass is also scaled because originally mass of the particle was 1. Because here it takes a value 1 if there is a particle at x at the time t. So, okay, so I didn't say, but now we consider the global Kawasaki dynamics that is denoted by eta nt. Probabilistically, it is a Markov process on the configuration space xn. So, it x runs over this discrete torus, and it takes a value 0 or 1 for each x and for each t. And then if it is 1, that means that there is a particle at x at the time t. Then the mass is considered as a 1 at the microscopic size. But we divide it by n to the d. So the n to the d is a volume size in the d-dimensional case. Then total mass becomes macroscopic. So, okay, so the microscopically mass is 1, but we divide by n to the d. Sorry, n to the d. Okay. And then mass for each particle has a very small mass. But in the total, so this is the sum over all the torus. Therefore, something like the order of the n to the d. So this one balances. So we want to keep some mass at the macroscopic level. So we introduce a spatial change in this way. So originally x runs over this discrete torus of the size n, but we just squeeze. We dividing x by n, squeeze the size, then it becomes a unit continuous torus. That is denoted by TD. TD is a unit torus at the macroscopic size, macroscopic space, continuous torus. Then this is a random measure on this space at a time t. Okay, so we introduce the time change, space change, and the mass change in this way. And also the generator is changed in this way. Okay, so our program is to study what happens for this process, or maybe this after scaling and introducing the we call it the macroscopic empirical mass distribution of this Glauber-Kawasaki dynamics. So the goal is to study the limit of this quantity as n goes to infinity. Okay, so then, okay, sorry, so it is hidden, sorry, so I don't know how to. Okay, so actually in the title, I put the non-gradient. So I just want to briefly explain what is the difficulty to consider the non-gradient models. So we want to derive certain nonlinear PD, which in the limit of this one, sorry. So we want to study the limit of this object as n goes to infinity. Then we want to show that the limit satisfies certain nonlinear PD. Okay, so then to derive such a nonlinear PD, we have to take a time derivative of this one. Time derivative of this one. So this is random measure, but we want to derive certain nonlinear PD, then the time derivative. So what we have to compute is the time derivative of this quantity first. But since this is a random measure, therefore we act certain test function, smooth test function. And then we compute the time derivative, but in the integrated form in time, which is also known as the Dynkin's formula. So essentially, we compute the time derivative of this quantity, but written in the integrated form. Then, just by acting the generator to this quantity, actually, we have this form. So we just skip, but we have this form plus randomness, which we denote by M. That sorry, so D is not necessary. So this is the integrated form. Therefore, sorry, so just remove D here. So this is called the martingale. So fluctuation term. But the fluctuation term is actually very small. Therefore, in the limit, we can neglect this one. So essentially, time derivative of this quantity is given by this object. And then, essentially, I only pick up the Kawasaki part, not the Glauber part is just ignore in this computation. I just pick up the Kawasaki part. And then by the time change, we have an n square in the Kawasaki part because we introduce a time change. Therefore, time derivative give an n square. And this form. Then phi is a smooth function, therefore 1n can be just put here. Then this gives, if you put n times this one, the y is the neighboring side. Therefore, then you have a gradient of the phi. Therefore, you can remove 1n. But the other n, we cannot remove because, and also actually this term is called the current. So one n can be absorbed in phi in the gradient form, but another n still survive. Therefore, this is called the current. And what if the current is a gradient of the certain function, which I call the h eta, then we can remove n. If this one has a gradient form, that is called the gradient model. Then essentially we can kill two n's if the current is a gradient of the certain function. But in general, it is not true. Then we need to replace this current by a gradient function under the large-scale space-time average. Actually, this is a very large time average because n is here, then actually from the microscope viewpoint, this gives a very long time average. And also, spatially, we have a big amount of the averaging because we divide by the volume. Okay, so this sum and n to the d balances. But we have another n. But we have to replace this current by the gradient function and the very large space average and also the very long time average. Actually, that was done by Baladan long time ago, actually the 130 years ago. So this is called the gradient replacement under the large scale space-time average. And okay, so in the Baladan's argument, we need so-called characterization of the closed forms. But Baladan's argument actually give only the qualitative hydrodynamic limits. So qualitative means this one converges to certain converges to a certain solution of the nonlinear PD, but only we can show the convergence, not the convergence rate. So in this talk, actually, we can prove also a quantitative hydrodynamic limit. That is a convergence rate, also much stronger than the Baladan's result. We can also prove the convergence rate of the hydrodynamic limit. But the method is inspired by the recent progress in the theory of the quantitative homogenization. In our case, we took the argument by Armstrong and his co-authors. So, non-gradient case, we have such difficulty, and also we can generalize a qualitative result to the quantitative result. That is what I want to explain today. Okay, so now I want to present our result. So, quantitative hydrodynamic limit and the interface motion. Okay, as I said, an interface separating sparse and dense phases is formed at the macroscopic level. And microscopically, this interface is vague. But if we move to the macroscopic level, we have a sharp transition from the sparse to the dense. And then this interface evolves under the anisotropic curvature flow. So we need several assumptions. The first one is the choice. It depends. It determine. It give as I said, a very subtle choice of the jump rate. Also this annihilation and creation rates. So I will explain later. But we need certain conditions for especially the choice of the creation and annihilation rates. And in the PD theory, it is known as a bistable and balanced condition for F. And from the Kawasaki case, we have a diffusion coefficient. So not just Laplacian, but we have a nonlinear Laplacian. So D and F this is a diffusion coefficient, nonlinear diffusion coefficient, and actually this is called the reaction term determined from the Glauber jump rate, flip rate, sorry. So this should satisfy certain relation. That is the first condition. And the second condition is we assume that certain entropy condition for the initial distribution of the Glauber-Kawasaki dynamics. So roughly, so initial distribution is close to the local equilibrium. Local equilibrium means a product measure, but profile may changes depending on the space. So initial distribution is close. So this means close to the local equilibrium situation with actually So H I don't write. Maybe I will write later. So this is called the entropy. Entropy behaves like a volume n to the d, usually in general. But it is smaller than the n to the d. That is the volume size minus kappa 1. Kappa 1 is a positive constant. So this means in-charge distribution is close to the local equilibrium. So we assume this one. And also from the PD viewpoint, we assume certain regularity of the initial value. And also certain technical conditions. And for the Glauber part, we put the Kn. This is the time change, and it depends on n. And this should go to infinity, but with a speed less than log n, but times delta. Delta should be small, constant. Therefore, this should behave like a log n, not n to the power some power rho, but log n. But anyway, so this goes to infinity. So we need such assumptions. Then this is in the still on the archive, not published yet. I hope it will be published soon, but still at the moment it is only in the archive. We have this convergence. And this is a macroscopic empirical mass distribution of the Glauber-Kawasaki dynamics. This converges to this function. This is actually the step function, rho minus or rho plus valued step function separated by interface gamma t, that is a hypersurface gamma t. And this converges rho plus or rho minus, but it depends on x, and it is separated gamma t. Maybe in the next page, I will explain more in more details. And this converges to this one in the L2 norm, in the randomness, in the probability space omega, but in the norm, the H minus alpha TD. This is a Sobolev space. Sobolev space, the usual in the L2 sense, with the usual Sobolev space with the exponent minus alpha. The alpha should be greater than d over 2. So actually, this is the sum of the delta function, delta measures. Okay, so maybe I can show you again. Rho n is the sum of the delta function times 0 or 1. So delta function belongs to this Sobolev space. Alpha is greater than d over 2. Therefore, this one belongs to this Sobolev space only when alpha is greater than d over 2. Therefore, we can prove only under this condition, because this belongs to this Sobolev space only when alpha is greater than d over 2. But anyway, under this Sobolev norm, we can prove this goes to 0. And we have certain convergence rate, which not just to 0, but with a certain convergence rate, which I want to explain later. Okay, so
with your
so
remark,
first,
sorry,
okay,
for
sorry.
with your
Yes.
remark, it means that the alpha is optimal.
Alpha is optimal. Yes, alpha is optimal. Yes.
Could you please comment what is the dynamic of interface? What is dynamic of separation surface? How it's moved?
Okay. Okay, so gamma t, I want to explain the next page, sorry. And also t is also determined, so t is not arbitrary, but in the short time. Also, I will explain in the next page, sorry. So, okay, so then gamma t, what is gamma t and what is this one and what is t? Okay, gamma t is defined in this way, and also gamma t. So first, let's consider the gamma t hypersurface. In the 2D case, it's just curve. and gamma t evolves under the anisotropic, that is a direction-dependent curvature flow. Actually, we will introduce certain nonlinear PD maybe later. Sorry. So, but with the anisotropy, mu is mu ij, n is a normal direction. So interface, you have a surface, and we only consider the smooth case. So let's assume the gamma t is smooth. Then the normal direction to the gamma t, that is denoted by n. N is
How do you
unit.
know it's always smooth over time? It should be proved actually that it's smooth. It's not assumption, it's a statement that it's smooth.
So we only consider the smooth case. So actually t is a time such that the flow has a smooth solution on the zero in the time interval 0 to t. So we only consider in the time interval. So this is just a short time result. After some singularity, usually some singularity happens, then we don't know. So let's assume that, okay, so at the time 0, it is smooth. So it is actually assumed here. Actually, that it is formed and a certain regularity. Therefore, gamma 0 is smooth. Okay, then I will explain the nonlinear PD which describe this curvature flow later, but we refer to the Giga's result, Giga Goto's result. We have in the small time, we have a smooth solution. Therefore, it is guaranteed that we have such T, which is positive. So, and sorry, I don't write now, but maybe later I will explain. So roughly, it depends on the direction, and then we have such quantity. Once this quantity, actually this quantity is determined from our microscopic system Glauber and Kawasaki rates, and then gamma t evolves under this anisotropic curvature flow. And especially if mu is isotropic, that is mu ij is some constant mu times delta ij. That is a unit matrix times some constant. In that case, we have a mean curvature flow. But since we have a Kawasaki part is more general, therefore, not only not necessarily the mean curvature flow, but the anisotropic curvature flow we have in the limit. Okay, sorry. So maybe just postpone how we can describe this anisotropic curvature flow later. And we have only the short time result until the smoothness is kept. And this Guzai gamma t is just inside of the gamma t, say, that takes the value of the rho plus, and outside of the gamma t, that it takes a rho minus. But actually, we consider on the torus, therefore the side is decided at the time 0, then continuously afterward, t positive. Okay, so but for this, we have to tune this f and the rate very, very precisely. Then rho plus and rho minus will be decided from this f and d. Maybe later. Sorry, so in the later. Okay, maybe in the next page. Okay, so the proof of this theorem is divided in two parts. The first one is a probabilistic part. In the probabilistic part, we approximate this. This is determined from the Glauber-Kawasaki dynamics, and we will prove this is close to the solution of this nonlinear PD. But still, this k depends on n. Therefore, this rho depends on n actually through k. Therefore, rho n and rho k both moving with n. So the distance, because between this one and this one goes to 0. That we can prove in the first step. That is the probabilistic part. And d rho, so usually, okay, d rho is the diffusion coefficient determined from the Kawasaki part. And the reaction term, F rho, is determined from the Glauber part. Glauber jump rate determines F rho. And we will prove that this is close to the solution of this nonlinear PDE, the solution of the nonlinear PDE in the maybe following way in the next page. And once we can prove this part, then in the second PD part, we can prove the solution of this nonlinear PD as k goes to infinity converges to this Guzai gamma t. That is a sharp interface limit for the nonlinear PD. So we separate into two parts. The first one is a probabilistic. Second one is purely PD result. Okay, so the first part. So we just compare this one and determined from the particle system. This is the solution of the nonlinear PDE. And we can prove, sorry, maybe, so this is just we compare macroscopic empirical measure and also the solution of the nonlinear PDE. And also, again, we just measure the distance under the Sobolev norm. And we have a certain convergence rate. Not just goes to 0, but we have a certain convergence rate. So this is a probabilistic part. Okay, so before doing that, I have to explain what is D rho and what is F rho. So D rho is determined from the Kawasaki part, Kawasaki jump rate. F rho is determined from the Glauber part. And the D rho is actually determined from the Kawasaki part, and it is called the Green-Kubo's formula in the statistical physics. And this one, actually, we discussed a long time ago with Uchiyama and Yao, a long time ago, 30 years ago. We already derived this diffusion coefficient from the Kawasaki, only Kawasaki dynamics of the non-gradient type, but only a qualitative result, not a quantitative result. Okay, so D rho is determined by certain variational formula. So first we consider this quadratic form, which depends on the test function f. F is also related to the local equilibrium situation, but anyway, f is now the certain function, test function, say. And first you fix the test function f, then we consider the quadratic form depending on rho and f by this average under the equilibrium measure. So this bracket means average. Okay, so this average under the equilibrium measure, that is a Bernoulli measure, nu rho, with a density, mean density rho. So this is, in a sense, a Dirichlet form. So this is a jump rate. And okay, so we consider such function. Then we take a variational formula, infimum, of this quantity in the test function f. That is called that determines the symmetric matrix C hat. Coefficient is determined by C hat rho divided by 2 times chi rho. Chi rho is given in this way, which is called the compressibility in the statistical physics. So this actually coincides with the formula known in physics called the Green-Kubo's formula, or maybe also we can call it the Einstein relation. So anyway, this one is determined only from the Kawasaki jump rate. And we can prove this is smooth and uniform. So we assume the non-degeneracy of this one. Therefore, D rho is actually non-degenerate and it is finite. Okay, so this was shown, I think, by Cedric first, a long time ago also. Okay, so this is a Green-Kubot formula. Then for F, sorry, so it is hidden. But for the F rho is determined from the Glauber part. And F rho is just the creation rate. So in the limit, so this if F is positive, then particle number goes up. That is, the creation rate is much large. Therefore, actually, in the microscopically, we have a creation rate and annihilation rate. Then we take a average of the difference of the creation rate minus annihilation rate. So if you have annihilation, then the particle density go down. Therefore, it has a negative effect. If you have a creation, then particle just increase, particle number increase. Therefore, it has a positive effect. Therefore, simply F is the average under so we call it ensemble average because this Bernoulli measure is the equilibrium measure. Okay, so F rho is given in this way. So we have to prove actually the certain ergodicity of our dynamics. Then we can replace a sample average actually by the ensemble average. That is the ergodicity. So we have to prove, but it should be locally in space and time. Therefore, it is called the local ergodicity. And then we have to assume to obtain the rho plus and rho minus. Now we assume these two conditions at the macroscopic level, but the first one is the bistability of this function F rho. So F rho has this shape, and it has 3 zeros. F has 3 zeros, rho minus, rho star in the between, and the rho plus. On the rho minus, at the rho minus and rho plus, it has the derivative is negative, this shape, and at the rho star, it has derivative slope is positive. Once F had this shape, then if the density runs from 0 to 1, say if the density is between, say, rho minus rho star, then F is negative. F is negative means it pushes to the negative direction. Therefore, if the density is around here, then F pushes to the negative direction to this density. Therefore, it goes to rho minus. And if around this area, and F is positive, then it pushes to the positive direction. Therefore, if the density is smaller than rho minus, then it tends to rho minus. Therefore, rho minus is a stable point. And the dynamics is determined by F. In the same way, rho plus is also stable point, but rho star is unstable point. So therefore, we have two stable points. Therefore, we call the bistable means two stable points. We assume this condition. So to have this situation, we have to tune this creation rate and annihilation rate carefully. And in addition, we have to assume the balance condition. Balance condition means F rho times the diffusion matrix. And it's averaging from the rho minus to rho plus, averaging and or the integral from the rho minus, rho plus. This should vanish as a matrix. So we have several conditions. This is not single condition, but every matrix element should vanish. And we can construct certain examples which satisfy these two conditions. Actually, the simplest case is just symmetric way we can construct certain example of the Glauber rate and also Kawasaki rate. So the Kawasaki rate also comes in to this condition.
But in this
Okay,
model,
so we assume this. Okay.
sorry,
Yes. Sorry.
in this
Yes.
model for which you can show the balance condition, it is because you are able to compute D of rho explicitly, or
Balance condition. Yes.
yes.
So
If you want to check it
if
in
balance
practice,
condition, sorry.
if you want to
So
check,
if balance condition is not satisfied, say if integral is negative, then rho minus is much stronger than rho plus. Therefore, eventually everything goes to rho minus. So so balance means
Yeah. I believe the balance condition fails, no phase separation can exist. Is correct, yeah?
so phase separation actually exists, but time change is different. I think time we have to consider much shorter time
Right.
because if balance condition is not satisfied, maybe say rho minus is much stronger than rho plus, then gamma t just shrink. But the time scale is different. Therefore, we have to consider different time scale. We have another one paper about this. So, but here we consider the rho minus and rho plus just balances. Balance means both have the same strengths in a sense. Then we have this situation, and okay, so in the unbalanced case, this dynamics is different, not the curvature flow, but just we call the Huygens principle. So this not curvature flow. Curvature flow means that you have to look at the second derivative around, but Huygens principle is just a single point for each point. It acts. So anyway, time change is time scale is different, and also limit this motion of the gamma t is different in the unbalanced case. But we have a certain result, but only linear Laplacian case because such unbalanced case we assume this is just linear Laplacian. But here we also consider nonlinear Laplacian case also. It's a certain technique. We have to solve certain problem to extend to the unbalanced case in this situation, but still it is not solved. Okay. So anyway, in this talk,
sorry, my
we
question,
assume
sorry, Tadaisa, my question
yes.
was, when you want to check the balance condition, you need to be able to compute D of rho.
Sorry.
You need to be able to compute D of rho. D of rho is not explicit in general. So when you say that you can construct some examples, it means that
yes.
it is because you can compute.
Okay. So to compute the D row is very difficult, I think.
Yes,
as you said, D row is difficult.
Yes,
So,
but when you said that you can
this
construct examples, you said you can construct examples. So these examples, example for which you can compute D of rho.
Not just symmetric. So in this example, we constructed the example that jump rate CXY is in a sense symmetric. So in the microscopically, it is symmetric.
Okay.
Then, so F has a symmetry and anti-symmetry, and the D has a symmetry. Then just cancels. So okay, sorry, I misunderstood your question. But otherwise, I tried to extend the non-symmetric case. I think it is possible by using the certain perturbation type result. But at the moment, I assume the symmetry. Okay, yeah, as Cedric said, to compute the D law itself is very difficult because it is given by a variational formula. Okay, sorry. And then okay, so then we can extract also the convergence rate. That is a quantitative hydrodynamic limit, so convergence rate. And this one was shown without Glauber part in this paper, just appeared on the CPAM quite recently, just online. So without Kawasaki part, then there is no K here, and also there is no F. And then we can prove this kind of result. But in today's talk, we also add the Glauber part. But the technique used here is very important to prove also Glauber-Kawasaki case. And the gradient case, this kind of the quantitative result was shown by, I think, several authors, for example, by Otto and others. They also considered this kind of result, and the kappa is much better than us. Our case kappa should be very small. But on the other hand, the alpha is just the best possible case in our case. But in their case, this is not really, and also in the only 1D case. So I expect by the maybe CLT result, I expect kappa should be something like a D. But we have several effects to determine kappa. Therefore, we don't reach to this level. But anyway, we can take kappa positive. That is true, but not the best possible. So this is a probabilistic part. And to show the probabilistic part, we use the relative entropy argument that was used already in the paper with Yao and Uchiyama. And we consider the entropy, relative entropy, which already appeared in the condition. Then actually we consider the relative entropy of our system. So we have a Glauber-Kawasaki dynamics. And its distribution is denoted, or maybe the density, but essentially the distribution is denoted by Ft. And we compare this one with local equilibrium state. But for the non-gradient case in the paper already in the Uchiyama and Yao, we introduced the second order approximation. So leading term, so this is denoted in the, described in the form of the Cramer transform. Actually, lambda is related to rho, but we choose under the Cramer transform. So essentially, if you neglect this one, then this part and this one is just 1/2 Bernoulli measure. Just neglect this second order term. Then this is just sum. Therefore, exponential. Therefore, it's a product. It's a product. Therefore, if there is no this term, then essentially the leading term is a product measure, and e to the lambda times eta x gives a certain measure on, say, one side. Therefore, it's a measure on the 0, 1. Then we can move from lambda to the rho. That is called the Cramer transform. By this transform, starting from lambda, we can move to the density rho by this formula. Then we choose lambda according to the solution of the nonlinear PD. Okay, PD3 is a nonlinear PD, given this one. So we first choose rho according to this nonlinear PD. Then we determine lambda by the Cramer transform to make the expectation of the under this measure becomes just a given rho. But just explicit transform we have. Then this term is not enough to consider the non-gradient case, then we need a second order approximation. Therefore, we put the 1 over n. So this is the first term, leading term. Then the next order term is a 1 over n. And then if we choose certain f, and actually by computation, we take a gradient of this function lambda and the inner product, then we can approximate the real system by this measure. So we compute the relative entropy of this real system with respect to this one, choosing lambda according to the PD, nonlinear PD 3 hydrodynamic equation. And we have to choose this second order correction term F more explicitly. Okay, and actually this F and F appeared in the variational formula for the Green-Kubo formula is actually the same. That becomes also clear later. So we had this F here. This F is a function of the eta, and we consider the variational formula for A in F, but another F appears, but actually the F should be the same in the variational formula and this second order approximation. And in the gradient case, actually we can take F equals 0. But the non-gradient case, F plays an important role. Then by the relative entropy argument, we prove the relative entropy of the real system with respect to the local equilibrium with the second order approximation, but choosing Fn in the proper way. Maybe in the next page, I will give a choice. What kind of choice? So this choice, under this choice, we can prove the relative entropy behaves like n to the d minus kappa. So n to the d is a volume order. Actually, entropy is always bounded by n to the d, constant times n to the d. But we have a minus kappa. Kappa is a positive constant. This means if t is close to this local equilibrium state with the second order approximation, we certainly need Fn to prove this statement. So this is quite probabilistic.
Sorry, this kappa is not kappa 1, the kappa 1 of the initial state.
It's different. Kappa 1, I assume that for the initial value, and
Yes.
kappa is determined from several factors. Also, it includes kappa 1 and other kappas. So this kappa should be much smaller than kappa 1. Okay. And once we can prove this one, then we can prove theorem 2. Actually, theorem 2 follows from this entropy bound by using the entropy inequality and also the concentration inequality, which is called Hofding's inequality. Just Gaussian tail estimate, something like Gaussian tail estimate. So once we can prove this estimate, then we have a theorem 2, indeed. So theorem 2 is this one. So once we have entropy bound, then we have this convergence rate. Kappa, this kappa is also maybe different from that kappa. Maybe it depends on other factor, but we can take kappa. So always I write a kappa, but maybe kappa changes. Okay, sorry.
Kappa
changes
depends on capital T, or not?
Sorry. So I think so. Capital T, yes, I think so. Maybe not. Sorry. Maybe, sorry. Capital T. This K depends on capital T, but kappa, maybe we can take uniform, I think. Sorry, I cannot. I cannot answer precisely, but probably. So here we don't use. So we don't. So this exists for all time t, all time t. But I think up to t. Yeah, I think kappa depends on t. Yes, because we just so. But here this t is different from the t in the theorem one, because the solution exists for all time, the nonlinear PD. But I think kappa depends on capital T, as Cedric asked. Okay, so but essential point is to prove this one. Then once we can prove this statement, then by these two inequalities, we can actually prove the theorem too. And yeah, Baradan's argument, as I said, the non-gradient argument, known for a long time, but it shows only this is a small of the volume, not strong like this one. So only this implies only the
So the relative
qualitative.
entropy, sorry, the relative entropy per site is tends to zero. Yes, it's to entropy
Yeah.
per site it tends to zero.
Yes. If you divide by n to the d, then entropy per site goes to zero. That is the Baradan's argument implied. But here, entropy by site is bounded by n to the minus kappa. This is stronger than this statement. Therefore, we have a quantitative result. And to prove that this one, so we follow the my result with Uchiyama and Yao long time ago, but we have to give this minus kappa effect n to the minus kappa. Therefore, we have to polish the proof, especially at all the place, but especially so we have to make more precise. We need much more fine error estimate is needed. For example, the Schauder estimate, it's okay, but one block is so we prove the local ergodicity, but the error estimate is needed to get the n to the minus kappa. So kappa appears from these all steps, but the minimum of the kappa determined from all steps is the kappa in the theorem. And also the defined Boltzmann-Gibbs principle, that is a gradient replacement, which I explained at the beginning of this talk. And this is the main point, actually, main point. And also the large deviation type upper estimate is needed, but we also need a precise estimate, precise error bound for the large deviation upper bound also. But the main point is this gradient replacement. And then we need a quantitative estimate for this gradient replacement. That is actually the main point of this talk. And then, to show the to show the quantitative gradient replacement or the defined Boltzmann-Gibbs principle, actually we use this result with Chen-Ing and also Han 1, which just appeared, and the convergence rate of this diffusion. So this divided by this one divided by chi-rho was called the diffusion coefficient, but it is this was given by as a variational formula for this one, and we need a convergence rate of this one. Once so f should have just this should be a local function. F0 means it depends on the bound eta in the bounded domain. Okay, but we take an infimum. Therefore, we have to just approximate from the finite volume. So this R is a range, the size of the range. So range size of the F. we approximate the size of the range is smaller than n, then so we just we can find such function f and eta in such a way that this approximation is the convergence rate is n to the minus certain constant alpha 2. Sorry, maybe there's some alpha 1, but okay. And then also the sup norm of this one is bounded by n square log n. So we can find, so this statement, so in this paper, we only consider the Kawasaki dynamics, but this one comes from the Kawasaki dynamics, and this statement was shown by using the argument from the quantitative homogenization. We can find Fn in this way. Roughly, Fn is just so the quadratic form for f was given in this way. It is a Dirichlet form, actually. Therefore, in a sense, it is also this first part is given by this way. Therefore, in a sense, this Fn is a projection of this one, but with the inner product given by this Dirichlet form. But to prove this one, actually we use the idea from the quantitative homogenization, and essentially we just borrow the idea from the quantitative homogenization by showing the Cacciopoli inequality and also weighted multi-scale Poincare inequality for the Kawasaki dynamics. So this is concerned only the Kawasaki dynamics. And the Cacciopoli inequality is something like inverse Poincare inequality. So to prove this, we use some iterative argument. So we consider the Dirichlet form in the finite domain. Then first by using the Cacciopoli inequality, that is Dirichlet form, we just estimate by using some boundary term. That's something like Stokes inequality, Stokes identity. Sorry. Then it is something like inverse Poincare inequality. Therefore, Dirichlet form bounded by certain L2 norm of the function. Then to come back to the Dirichlet form, we apply the Poincare inequality, but Poincare inequality itself is not enough. Therefore, so-called the multi-scale Poincare inequality is needed to make a Poincare constant better. Maybe in the next page, I can explain what the idea of the multi-scale Poincare inequality. And then just iterative argument, just give this estimate. We can find such function. Okay, so what is a multi-scale Poincare inequality? Maybe just feeling. So Poincare inequality is just L2 norm, but with a mean 0. So we consider the box, the large box is a side length L, capital L is a 3 to the power m. So we have a large box. Sorry. And then we divide into the small boxes. That is a box n. N runs from 0 to m. So small boxes. And the L2 norm is bounded by the Dirichlet form. That is Poincare inequality. In the Poincare inequality, so gradient is something like just determined from the Kawasaki exchange operator, but with we give some sign. But essentially, it is a Kawasaki exchange operator. Therefore, usual Poincare inequality is L2 norm with a mean 0 is bounded by the Dirichlet form. That is this one squared and making the sum over all bonds. And the number of the bonds is just parallel to this one. Okay. So, but then in the Poincare inequality, we need L square times this one. But that is L square is too large actually. Okay, so how to modify this Poincare inequality? So this is so we divide into the large box into the small boxes, and maybe starting from M. M is just we don't divide into the volumes into the small boxes. And then in the M case, then 3 to the power m is just length. Then you have a square. Therefore, L square. That is the usual Poincare a constant for n equal m case. However, in this estimate, we have a sum of the exchange operator. Not each piece, but we first make a sum, average here. Therefore, even if the constant is L square, but we have a sum. So it helps. It helps a lot because this sum gives some certain cancellation. Okay. Then, but each piece means n equals 0 case, just you divide into small pieces. That correspond to n equals 0. N equals 0 case, we have each piece, so single, this one is just square. However, the constant for this each piece squared is just 3 to the power 0, just constant. That is very small to compare to the L square. Therefore, the constant is improved in a sense compared to the classical Poincare inequality in this estimate. That is the idea of the multi-scale Poincare inequality. Then improving this, so I think this is one of the main point in the quantitative homogenization. So we just borrowed the idea from that. Then we proved this for the particle system. And then we applied this. Then we derived such kind of convergence rate for the diffusion, essential diffusion coefficient. Okay, then the PD result. So this was okay. So maybe the time I spent too much time. Maybe is it okay?
Yes, it is okay.
So sorry, too much time maybe. Then I didn't explain the anisotropic curvature flow. So anisotropic curvature flow is actually described in this way by using the signed distance function d, tv. So signed distance function means, okay, so now we want to derive starting from this one, rho depends on k, but rho k converges to the step function, sorry. This one. And signed distance function means distance from the gamma t. And maybe rho plus side, it is distance is positive. So you have a point x inside gamma t, but the distance to the gamma t is positive. But if the position x is outside, then in this region, then the sign, distance is negative. That is called the sign distance. That is denoted by d. Sorry. So then d, then we can write the equation for d. So d is distance from, but with a sign, plus or minus. Then we can give the anisotropic curvature flow in terms of the evolution of the sign distance function in this way. So this is a fully nonlinear equation. And as I said, mu ij is just a delta ij times constant, then it's a mean curvature flow. So, but we have a direction dependent. So gradient D give some the normal direction. Therefore, the direction dependent PD we have. And then with Hyunjin Park, we solved this problem. So this converted to the step function separated by a gamma t, and the gamma t evolves under this anisotropic curvature flow. And anisotropic curvature flow was already studied by Giga and Goto, and they proved the local in time well-posedness for this equation. So as long as this equation has a smooth solution, we can prove this one by using the comparison argument. We constructed the super solution, sub solution, sandwiching this one by super and sub solution, and super solution, sub solution converges both to this object. Therefore, this one converges to this one. So we essentially apply the comparison argument.
But
So
in
this
dimension
one,
one, sorry, in dimension one, it is not a global in time, the solution, or
okay,
just
so
restriction?
we assume that this is greater than 2, okay, greater than 2 or equal to 2 in this argument. But in the 1D case, actually,
don't know, for example, for auto, auto is a dimension one, so
okay, yes. 1D is much easier, I think, but we didn't carefully study it. 1D case is there is no curvature actually. I think
yeah.
I think it is stopped. I think in the 1D case. So maybe okay. So you are right. I think I wrote somewhere D is greater than 2 or equal to 2.
Okay.
We need such assumption. Otherwise, it's trivial. I think in the 1D case, by the balance condition, gamma t stop. It never move. I think so. In the unbalanced
It will
case,
not be totally trivial because auto is in dimension one.
okay, yeah.
The result of auto is in dimension one, so I think it is not totally trivial.
But this one under the balance condition,
Okay,
gamma
yes.
t doesn't move in the 1D case.
Mm.
But of course, you can consider unbalanced case. Then this moves. I think so. If d equal 1, gamma t doesn't move because curvature is 0 in a sense. The 1D surface is just flat surface. Therefore, it doesn't move. Therefore, we assume d is greater than or equal to 2. Otherwise, this becomes trivial. Of course, this is even if gamma t stops, I think it is interesting, but in a sense, this part becomes trivial in the 1D case. Okay. Okay. Thank you for asking. Okay, then yeah, and this result is new. I think Laplacian. So sharp interface limit is very well studied when the leading term is Laplacian, linear Laplacian case. But the nonlinear case is actually, I think it is not studied before. So if D is just delta ij, then you have a linear Laplacian. The linear Laplacian case is quite well studied, but nonlinear Laplacian, this is a nonlinear Laplacian. Then I think we cannot find any difference for this case. Therefore, I think it should be new in the PD viewpoint. This result should be new. Okay, so but anyway, by combining this result and also the probabilistic part, we conclude the proof of the hydrodynamic limit, the theorem one, and we can conclude the proof of this one. Okay, the last part I also discussed the fluctuation with Claudio Landim and also Sundar Sesraman. So still this is not well studied, I think. We assume the Kawasaki part is simple. Simple means jump rate Cxy is just constant. Then the nonlinear diffusion term becomes a Laplacian. And also the interface is not curved, just flat. Therefore, it is immobile. Immobile means under the curvature flow, it cannot move because it is flat. Already curvature is zero. Then there is no drift acting to gamma t. Therefore, it doesn't move. So in this situation, we have this situation. So the interface is flat, and this separate dense area and the sparse area. And the fluctuation is very small. Therefore, we have to stretch to the normal direction to observe the fluctuation of the interface. Then we need another scaling to observe the fluctuation. Then we introduce another scaling, especially we separate into the normal direction and also tangential direction. This X bar means a tangential direction, and the Z means a normal direction. And then we need some scaling in the normal direction in this way. Then we consider the fluctuation, but this scaling is not enough. This is the usual CLT scaling, but we have to multiply another scaling corresponding to this one. Then the correct scaling should be like this one. And also we have to subtract once you just making the scaling for this normal direction, then this converges to essentially to the certain transition layer. Transition layer is given by this function, but to the normal direction. That is actually the standing wave solution correspond to this one. So we have a simple Laplacian, then this is a normal direction, therefore one-dimensional Laplacian plus the reaction term. Then so it satisfies the balance condition. Then we have a so-called standing wave shape. Then we consider this psi. Then we proved the joint paper with Claudio and Sundar. Only 1D or 2D, and K should be less than delta times log n square root log n. Then essentially the fluctuation converges to described by certain stochastic PD. In the low large number case, we don't have the fluctuation, but by this stretching, we observe the fluctuation term. Then roughly for each point, we have a certain fluctuation, and then fluctuation is given by independent one, but we have a Laplacian to the tangential direction. We have this one. So, but we need some constraint for this condition for d equal 1 or 2. In fact, to prove the fluctuation, we have to prove much more than before. For the hydrodynamic limit, we may prove this is a small o of the volume, like Baladan did. Not Baladan, but with Uchiyama and Yao, we did. N to the d is enough, but for the fluctuation, we have to we need a much stronger result to just control actually this one to control this factor. So that gives some constraint for the dimension t equal 1 or 2, and also k should be much smaller. So originally it was a delta times log n, but we need a much stronger assumption. Then we can derive this linear PD. And I have as I said, I have several other conjecture to derive the nonlinear SPD, but still it's difficult. Okay, so sorry, I took too much time. And we discussed the quantitative hydrodynamic limit, phase separation from the Glauber-Kawasaki dynamics. And the Kawasaki part was especially the non-gradient type. And we have to choose the creation, the annihilation rates properly tuned. We have to tune very precisely. Then we have a situation that sparse and dense phases with particle density rho plus and rho minus appears. And we derive the anisotropic curvature flow. And as a fluctuation, but a very special case, we derive the linear stochastic PD. Thank you very much for your attention. Sorry, I think, took too much time.
Thank you very much. Thank you. I don't know if there are some questions.
Could ask a question. I wonder what kind of general condition would guarantee that the phase separation surface moved with some guaranteed speed. For example, if we look for the simplest model, something like KPP Fisher equation, then the classical effect that the traveling wave cadence propagates slowly than the square root of 2. What kind of general assumption would guarantee that the surface moved with some minimal speed?
Okay. So that is interesting question. I think we don't study very carefully, but we have in the unbalanced case, we have something correspond to the what Jürgen Geltner did a long time ago. That is an unbalanced case, but that is a bistable case. As you said, the KPP is a monostable case. Monostable case is, I think, much more difficult, but it should be interesting to study because speed is not uniquely determined for the monostable case. So actually, I don't know, but Geltner studied a bistable case, but unbalanced case, which is not a KPP case, but we can derive a different motion for the gamma t. That is Huygens principle. That is, we have a such result also correspond to the unbalanced case, but not KPP type.
I have some questions. Okay, in dimension 1, you know there exist some models for which the fluctuation dissipation relation is explicit. I mean the decomposition of the current into some gradient term plus some fluctuating term. Is it also there are some explicit case in dimension bigger than 1 or not? You see which models I am. In dimension
So
1, I know it is possible. But in dimension 2, I don't know if they are existing, but just to see if you can, how sharp are your results, in fact, because if the fluctuation dissipation is exact, probably you can improve the results.
I see.
But I don't know if in dimension bigger than 1, it is possible to construct such models. It is not so clear.
I see, but I don't know. But once I discussed with David, but he probably he said he doesn't know in the higher dimensional case is more difficult, and that is what I heard from David. So sorry, I have no, but in the 1D case, okay, it's interesting to have this decomposition. I see. Okay, thank you.
And some other question is phase K. So you assume that it is very big with respect to 1 and very small with respect to n square. So what do you expect in the limiting cases? You expect something similar or something very different?
Okay, maybe we can go to the some power of the n, not log n. But we apply the Yau's relative entropy method, we apply the Gromwall inequality that gives some restriction to K. Therefore, we have to assume the K is smaller than delta times log n. But in reality, maybe we can go much more than that, and to some power. Certainly not. Power should be, of course, smaller than 2, but maybe I don't know how much we can go up. But anyway, by this method of the Yau's method originally, give the restriction to the constant k.
And some other question is about, so in fact, you say that we can provide some alternative proof of hydrodynamic limits for non-gradient models, avoiding this decomposition, not the decomposition, but the description of the closed forms.
Mhm.
Is it
Yes.
correct? And how
Yes, yes.
robust is this method? I mean, if you don't consider this Kawasaki dynamics, but I don't know, some other system, you need to prove some weighted Poincare inequality, which probably
Yeah,
is
yes.
quite robust.
Mhm.
But the other
Yes.
inequalities that you mentioned, this, I don't remember the name, Cacciopoli
Cacciopoli,
inequality.
yes. Mhm.
This is something which is very particular to the model, or it is...
So we are studying now. So at the moment, we only have this Kawasaki case, but the natural model is, of course, generalized exclusion process. That is not 0, 1, but 0, 1 to maybe up to k. That is a generalized exclusion model, which is also the non-gradient. That actually I'm discussing with Nagahata, and he said maybe in the 1D case he can prove, but at the moment the proof is not completed. But we are trying to extend to other models, non-gradient models.
Okay. So I don't know if there are some other questions. Maybe not. Okay, so thank you again. I know that now
Thank you
it's
very much.
late for you. In principle, you should have started at this time, but
Sorry. Thank you very much for
no,
shifting
it's not a problem.
2 hours earlier.
Yes, it is already very late. Okay, so
Sorry,
thank
I
you
took
very
too
much.
much time.
Thank you. Okay, have a good
Okay.
night.
Okay, good night. Thank you very much for joining.
Bye-bye.
Bye.
It's very, very late now in
Just
Japan.
because it's in